This is a video for AQA Discrete Mathematics. This is Graphs and Networks section 2, where we're looking at the travelling salesperson problem, and this is 2.2, where we're looking at in particular finding an upper bound for the problem. Well, remember from the first video on this section we talked about the idea of an upper bound being a solution that we knew was a reasonable solution to the problem. However, we didn't know whether it was the best or not, the optimal tour. But at least it is a solution. So what we want to do is to see, well, is there a methodical way of finding such a tour so that we can easily computerize that. One method that is used is something called the nearest neighbor algorithm, and this is what we're going to discuss in this particular video. So the nearest neighbor algorithm produces a tour, not necessarily the best or the optimal tour, but at least it's one that works, and therefore we can say that it is an upper bound for the optimal tour. Well, the nearest neighbor algorithm is another one of these sort of greedy algorithms, very similar to Prim's, but differs in one very crucial way. So it says start at any vertex, which is basically the same as Prim's, but then it's the next bit. It says from the vertices that have not already been selected, find the nearest. So we go to the nearest one. Well, that I suppose is the same as Prim's, but then we keep going to the next one. So whereas in Prim's algorithm you were looking at the whole tree that was developing and deciding which is the nearest to the tree, this time you're going from point vertex to vertex. So you're going to one vertex and then on to the next one. So never looking at all of it, you're simply looking at the last one that you've reached. Find its nearest that hasn't been added to the network as yet. And once you've selected all of the vertices, you then go back to the first one. So a greedy algorithm, very intuitive. So it doesn't necessarily find all of the possible Hamiltonian cycles, but we can also apply it to a network which is not complete, in which case we have to do a little bit of adjustment to the incomplete network for us to get it to work in all cases. Well, let's look at an example of that then. Here's a very simple complete network with 5 vertices and their weights. That we were thinking about them as distances, but remember that the weights can be representative of all sorts of things. Might be costs, might be time, for example. But we want to find the tour going around here, starting and finishing at a vertex, and trying to find a least weight tour, or at least finding a tour with the smallest that we can, remembering that we haven't necessarily got every single tour by this method, but at least we can find our upper bound. Well, let's give that a go then, and the first one starting at A. So if you look at A, you can see that the nearest one to it is B, so we're going from A to B, and that is length 8. And then from B, the nearest one is E, and that one is of weight 7. And then from E to D, weight 8. D to C, 14. Now we've finished all of our vertices, so all we have to do now is to get back to where we started, to A, and that is 13. So if you work out the total of those, you find that it's 50, and the tour is A, B, E, D, C, and then back to A. Or we could start at a different vertex, so this time for example at B, and from B we would go to E, which is of weight 7, then to D, which is of weight 8, And then from D, then the closest one then is A, which is 11. From A to C is 13, and then finally get us back to B, which is 9. So if you add those up, you find that we've actually there got a total of 48, and the tour is B, E, D, A, C, B. What I'd like to do now is for you to pause and choose other starting vertices. You can do them all if you wish. You can start at E, C and D, or perhaps you just choose a couple, but have a go and see what the tour are that you get and the weights of those tours. So pause the video, and when you finish, we'll go on to the next slide. Right, so just a reminder then of what's going on. We choose any vertex as the starting point, and from all those vertices select the next nearest one, repeat until we get all of them joined in, and then go back to the start. So each time we're going from point to point, not looking back really, which is what we would have to do if we're applying Prim's algorithm for minimum spanning tree. Now what we can do is to repeat that for different starting vertices and choose the smallest of those. So what we're trying to do, remember, is for the upper bound, which all of these are upper bounds, we're trying to move that upper bound as small as possible. So the least upper bound is the best of the upper bounds that we've got. But do remember that we still don't know that it's necessarily an optimal tour, because this doesn't find all of the tours in a network. All we know is it's a good or a better upper bound than we had with larger ones. So there we are. Those are the results from all of these starting points. You can check whether you've got those correct or not. Now in particular, one of the things to note is that you don't necessarily get a different tour even. So for example, in this one you can see that B and C are basically the same. So starting at B and looking at that, if you go from there, if you start on this tour working here, you can see it goes C, B, E, D, A, C. So it's basically the same one as the one below, but just starting at a different point on the list. And you can see that A and D are actually the same tour, but going in the opposite direction. So if you start at this point here and go back in that direction, it goes D, E, B, A, C, D, which is exactly what we've got this one. So this method might look as though we've got 5 different solutions, but in fact we haven't. So they are repeats of each other. However, we can say that the best tour that we've got here, the one with least weight, is of size 48. So what we can say is that our optimal tour is less than or equal to 48. So the optimal tour is less than or equal to 48 is what we conclude from our work so far. Now it's very important that you understand that we haven't checked every single possible Hamiltonian cycle. So remember, if we had 5 vertices, then we have 4 factorial over 2 different cycles. So there are in fact 12 of them, and we've only found from there. In fact 3, wasn't it, because we had some that were repeated. So just to reiterate then, so far we've said that the optimal tour is less than or equal to our smallest upper bound. So in this particular case that was equal to 48. So we know that the optimal is less than or equal to 48 from the work that we've done. It's possible to do the nearest neighbour algorithm on a matrix. So again, very similar to Prim's, but this time we just look at the next column each time. So let's try it with this. So we start off, let's say, at A, so we label that number 1, look down the column, find the smallest, which is that one E, and delete those 2 rows. Delete the rows for A and E and label E as being the second one. Probably worth keeping track of our route then. We're going from A to E, and that one is of size 1. Then we look down from E to find the smallest. Remember, only looking at that new column. Smallest there is 1, and it's going to F. So that becomes the third one that we've added. Delete the row there. Next one in column F is 2, which is at C. That becomes the fourth one that we've added. Delete that row. From C, looking down, then the smallest is D, which is 1. Delete that row. D becomes the fifth one to be added. There's now only one left, which is to get to B. And that is 5. And then do remember that we've got to get back to our starting point. It's one thing which is often forgotten, which is that 3, because that was our 6th point to be added, but the 3 to get us back to A is vital. So that the total that we have then is just the sum of those, and if you add those up you'll see that the tour has got a weight of 13. So very similar to Prim's, but differs because instead of looking at every single column, you're simply looking at the latest column to be added. Well, that's the end of this video looking at upper bounds, and in the next one we'll look at finding a lower bound solution for the TSB problem.